In the vast expanse of space, where time stretches into epochs and distances defy comprehension, two remarkable comets are making their way toward us. 1. C2025 R2 SWAN has spent the last 40,000 years traveling inward from the distant reaches of the Oort Cloud, a frozen reservoir of primordial material at the edge of our solar system. The other, 3I Atlas, is an interstellar traveler, a visitor from the depths of the Milky Way galaxy, with a journey spanning billions of years. Both comets offer a glimpse into the mysteries of the cosmos, of ancient origins, cosmic forces, and the fleeting beauty of celestial wanderers. Their paths, though vastly different, converge briefly in our skies, allowing scientists and stargazers alike to witness a rare cosmic event. Comets have long captured the imagination of humanity. Ancient civilizations saw them as omens, while modern science views them as time capsules from the early solar system. C2025 R2 SWAN represents the enduring legacy of our cosmic neighborhood, a remnant of the building blocks that formed the planets. Its journey from the Oort Cloud, a hypothetical sphere of icy bodies surrounding the Sun at a distance of up to tens of thousands of astronomical units, has taken millennia to reach the inner solar system. In contrast, 3I Atlas is a true interstellar traveler, originating from a location far beyond our solar system, moving through space at speeds that defy gravitational capture by the Sun. While C2025 R2 SWAN is a familiar type of comet, its eventual disintegration adds an element of unpredictability to its story. Meanwhile, 3I Atlas offers an unprecedented opportunity to study a comet from outside our solar system, providing insights into the conditions of distant star systems. What sets these two comets apart is not only their origins, but also the scientific significance of their encounters with the inner solar system. C2025 R2 SWAN provides valuable information about the structure of the Oort Cloud and the processes that send comets toward the Sun. Its disintegration raises intriguing questions about the stability of cometary nuclei and the factors that lead to their breakdown under intense solar radiation. On the other hand, 3I Atlas challenges our understanding of interstellar objects, offering a rare chance to analyze the composition of a body that has traveled from another planetary system. With an estimated age of 7 billion years, 3I Atlas could be older than the solar system itself, making it a relic from a time when the Milky Way was young. By studying these comets, we gain a deeper appreciation for the dynamic nature of our cosmic neighborhood and the interconnectedness of the universe. This video will explore the fascinating journeys of C2025 R2 SWAN and 3I Atlas, delving into their origins, their paths through the solar system, and the scientific insights they provide. From the distant Oort Cloud to the vast expanse of interstellar space, these comets serve as messengers from the past, carrying clues about the formation of the solar system and the nature of the universe beyond. As we embark on this cosmic voyage, we will uncover the stories hidden within their icy nuclei and the lessons they offer about the grand scale of time and space. To truly grasp the significance of C2025 R2 SWAN and 3I Atlas, we must first understand the cosmic environments from which they originate. The Oort Cloud, a theoretical shell of icy objects that surrounds the solar system at a distance of approximately 20,000 to 100,000 astronomical units AU from the Sun, is believed to be the source of long-period comets like C2025 R2 SWAN, named after Dutch astronomer Jan Oort, who first proposed its existence in 1950. The Oort Cloud is thought to contain trillions of icy bodies, remnants from the early solar system that never coalesced into planets. These objects remain in a state of deep freeze, untouched by the Sun's warmth, until gravitational perturbations from passing stars, galactic tides, or even the hypothetical Planet 9 send them hurtling toward the inner solar system. C2025 R2 SWAN is one such object, having spent the last 40,000 years on an outbound journey from the Oort Cloud. Its trajectory suggests that it was nudged from its distant orbit by some external force, setting it on a path toward the Sun. Once it entered the inner solar system, the comet began to experience the effects of solar heating, causing its volatile ices to sublimate and form a glowing coma and tail. The process of outgassing is a defining characteristic of comets, and it is this transformation that allows us to observe them as they travel through space. However, not all comets survive their close encounter with the Sun. In the case of C2025R2 SWAN, observations indicate that the comet may have disintegrated in mid-April 2025, leaving behind a cloud of dust and debris. This disintegration is not uncommon for comets that venture too close to the Sun, as the intense heat and tidal forces can cause their fragile nuclei to break apart. While C2025R2 SWAN hails from the Oort Cloud, 3I Atlas tells a different story, one of interstellar origins. Unlike comets that originate from within the solar system, 3I Atlas is an interstellar object, meaning it did not form in our cosmic neighborhood, but rather in a distant planetary system. Its trajectory is defined by a hyperbolic orbit, a path that is not bound by the Sun's gravity and will eventually carry it back into interstellar space. The discovery of 3I Atlas marks a significant milestone in astronomy, as it is the third interstellar object ever identified in our solar system, following the enigmatic 1I Oumuamua and 2I Borisov. What makes 3I Atlas particularly intriguing is its estimated age between 7 and 14 billion years, suggesting that it predates the formation of the solar system itself. This places its origin in the early stages of the Milky Way's evolution, a time when planetary systems were forming and interstellar space was still relatively young. The journey of 3I Atlas is a testament to the vast timescales involved in cosmic phenomena. Originating from the direction of the constellation Sagittarius, near the galactic center, the comet has traveled through the Milky Way for billions of years before crossing into our solar system. Its arrival is not random, rather, it is the result of gravitational interactions within the galaxy, which can eject objects from their home planetary systems and send them drifting through the void. The fact that 3I Atlas has remained intact for such an extended period is remarkable, as interstellar space is not a forgiving environment. The comet must have survived the harsh conditions of deep space, including exposure to cosmic radiation and the occasional gravitational disturbance from passing stars or molecular clouds. One of the most striking aspects of 3I Atlas is its high velocity, over 58 kilometers per second, relative to the Sun. This speed is significantly greater than that of typical solar system comets and is a clear indicator of its interstellar origin. The hyperbolic excess velocity, or the speed at which an object moves relative to the Sun after accounting for gravitational interactions, is a key factor in determining whether an object is truly interstellar. In the case of 3I Atlas, its velocity is so high that it will escape the solar system entirely, continuing its journey through the galaxy. This distinguishes it from comets like C2025R2 SWAN, which will return to the Oort Cloud after completing its orbit. The discovery of 3I Atlas also raises important questions about the prevalence of interstellar objects in our solar system. Until recently, such objects were considered rare, but the detection of 3I Atlas suggests that they may be more common than previously thought. This has implications for our understanding of planetary formation and the exchange of material between star systems. If interstellar comets are frequent visitors to our solar system, they could provide valuable insights into the composition of other planetary systems and the distribution of volatile materials throughout the galaxy. Both C2025R2 SWAN and 3I Atlas exemplify the dynamic nature of the cosmos, demonstrating how objects can travel across immense distances over thousands or even billions of years. While their origins differ, one emerging from the depths of the Oort Cloud, the other arriving from the far reaches of interstellar space, both comets offer a window into the fundamental processes that shape our universe. By studying their trajectories, compositions, and behaviors, scientists gain a deeper understanding of the forces that govern the movement of celestial bodies and the evolution of planetary systems. As we delve deeper into the journeys of C2025R2 SWAN and 3I Atlas, we uncover the intricate dance of celestial mechanics that governs their paths through space. Each comet follows a distinct trajectory, shaped by the gravitational influences of the Sun and the planets, as well as the unique circumstances of its origin. Understanding these trajectories provides insight into the forces that dictate the motion of objects in the solar system and beyond. C2025R2 SWAN originates from the outer reaches of the solar system, specifically from the Oort Cloud, a distant reservoir of icy bodies. Its trajectory is classified as nearly parabolic, indicating that it is on a long-period orbit that brings it close to the Sun before sending it back into the depths of space. The comet's orbital period is estimated to be anywhere between 1,400 and 20,000 years, depending on the accuracy of the data used for calculation. This wide range underscores the challenge of precisely determining the comet's future path based on limited observations. As C2025 R2 SWAN approached the inner solar system, it reached a perihelion, the closest point in its orbit to the Sun, on 12 September 2025, at a distance of 0.5 AU, 75 million kilometers. At this point, the comet was subjected to intense solar radiation, which triggered the sublimation of its volatile ices, forming a coma and tail that made it visible to observers on Earth. In contrast, 3I Atlas follows an entirely different kind of trajectory. As an interstellar object, it is on a hyperbolic path, meaning it is not gravitationally bound to the Sun and will ultimately escape the solar system. This trajectory is characterized by a high orbital eccentricity of 6.141, making its path appear almost straight rather than curved. The comet's speed relative to the Sun is an impressive 58 kilometers per second, placing it among the fastest interstellar objects ever observed. This high velocity is a direct consequence of its interstellar origin, as it has not been influenced by the gravitational forces of the solar system in the same way as comets like C2025 R2 SWAN. Instead, 3I Atlas's trajectory is shaped by the galactic gravitational field and the initial velocity it carried when it was ejected from its home planetary system. The distinction between parabolic and hyperbolic trajectories highlights the fundamental difference in the nature of these two comets. Parabolic trajectories, like that of C2025 R2 SWAN, represent the boundary between bound and unbound orbit. Objects on such trajectories are loosely held by the Sun's gravity, allowing them to return to the outer solar system after their closest approach. In contrast, hyperbolic trajectories, like that of 3I Atlas, indicate that the object has enough kinetic energy to escape the Sun's gravitational pull entirely. This distinction is crucial in determining whether an object is native to the solar system or an interstellar visitor. The velocity at which each comet travels is another key factor in understanding their journeys. C2025 R2 SWAN moves at a relatively moderate speed compared to interstellar objects, as it is still under the influence of the Sun's gravity. However, its velocity increases as it approaches perihelion, reaching a peak before slowing down again as it moves away from the Sun. 3I Atlas, on the other hand, maintains an exceptionally high speed throughout its passage through the solar system. Its hyperbolic excess velocity of 58 kilometers per second is significantly higher than that of previous interstellar objects, such as 1I Oumuamua, 26 kilometers per second, and 2I Borisov, 32 kilometers per second. This extreme speed is a direct result of the comet's interstellar origin and the gravitational interactions it has experienced as it traverses the galaxy. Beyond their trajectories and velocities, the paths of C2025 R2 SWAN and 3I Atlas also bring them into contact with various planets in the solar system. C2025 R2 SWAN passed by Saturn at a distance of approximately 0.8064 AU on 29 January 2023, but this encounter had little impact on its overall trajectory. The comet's closest approach to Earth occurred on 19 October 2025, at a distance of 0.26 AU, 39 million kilometers, making it a notable but not particularly close visitor. In contrast, 3I Atlas's trajectory brings it into proximity with multiple planets. It passed by Mars at a distance of 0.19 AU, 28 million kilometers, on 3 October 2025, and will pass by Venus at 0.65 AU, 97 million kilometers, on 3 November 2025. These encounters, while not close enough to pose a threat, offer opportunities for further observations and studies of the comet's behavior as it interacts with the gravitational fields of the planets. Despite their differences, both comets are subject to the same fundamental laws of physics that govern the motion of objects in space. Gravity plays a central role in shaping their trajectories, with the Sun's immense gravitational pull dictating their paths through the solar system. For C2025 R2 SWAN, the Sun's gravity is the dominant force, guiding its return to the Oort Cloud after its brief foray into the inner solar system. For 3I Atlas, the Sun's gravity acts as a temporary obstacle, slowing the comet slightly before it continues on its journey beyond the solar system. The study of these comets not only expands our understanding of celestial mechanics, but also provides valuable insights into the conditions of their respective origins. C2025 R2 SWAN offers a glimpse into the Oort Cloud, revealing the mechanisms that send comets toward the inner solar system. Its eventual disintegration raises questions about the stability of cometary nuclei and the factors that contribute to their breakdown under intense solar radiation. 3I Atlas, on the other hand, serves as a messenger from another planetary system, carrying with it the chemical signatures of its home environment. Observations of its composition, particularly the presence of carbon dioxide and water ice, provide clues about the conditions in which it formed and the processes that shaped its journey through interstellar space. As we continue to track the movements of C2025 R2 SWAN and 3I Atlas, we are reminded of the vast and dynamic nature of the universe. These comets, though fleeting in our skies, are part of a much larger cosmic narrative, one that spans millennia, galaxies, and the fundamental forces that bind the universe together. The journeys of C2025 R2 SWAN and 3I Atlas extend beyond their individual paths through the solar system. They offer profound insights into the nature of comets, the evolution of planetary systems, and the interconnectedness of the universe. As we examine these two comets in greater detail, we uncover not only their unique characteristics, but also the broader implications they hold for our understanding of celestial bodies and the forces that shape their trajectories. Comets have long been regarded as relics from the early solar system, preserving the building blocks of planets in their icy nuclei. C2025 R2 SWAN, like many other long-period comets, is a product of the Oort Cloud, a distant reservoir of frozen material that has remained largely undisturbed since the formation of the solar system. The fact that it has taken 40,000 years to reach the inner solar system underscores the slow and deliberate nature of cometary migration. This journey is not a linear one. Rather, it is shaped by gravitational perturbations from passing stars, the galactic tide, and even the hypothetical Planet 9, which could nudge comets from their distant orbits. The disintegration of C2025 R2 SWAN as it approached the Sun raises intriguing questions about the fragility of cometary nuclei and the conditions under which they survive. Some comets endure their close encounters with the Sun, shedding material but remaining intact, while others, like C2025 R2 SWAN, break apart under the intense heat and tidal forces. Studying such events helps scientists refine their models of cometary behavior and better predict the fate of future comets that may follow similar paths. 3I Atlas, in contrast, presents an entirely different set of scientific inquiries. As an interstellar object, it is the first known comet to originate from outside the solar system, making it a rare and valuable subject of study. Its trajectory, defined by a hyperbolic orbit, indicates that it is not gravitationally bound to the Sun and will ultimately escape the solar system, continuing its journey through interstellar space. The comet's high velocity, over 58 kilometers per second, relative to the Sun, confirms its interstellar origin, as no object within the solar system can achieve such speeds without external gravitational assistance. This speed, combined with its unusual composition, challenges existing theories about the formation and evolution of comets. The presence of carbon dioxide and water ice in 3I Atlas suggests that it formed in a cold, distant region of its home planetary system, where such volatile compounds could condense into solid form. Comparing the composition of 3I Atlas with that of comets from the solar system provides valuable insights into the diversity of planetary environments and the processes that shape the development of celestial bodies in different star systems. The study of 3I Atlas also sheds light on the age and origin of interstellar objects. Based on its trajectory and velocity, scientists have estimated that 3I Atlas could be between 7 and 14 billion years old, making it significantly older than the solar system itself. which is approximately 4.6 billion years old. This suggests that the comet originated in an earlier phase of the Milky Way's evolution, when planetary systems were forming and interstellar space was still relatively young. The fact that 3I Atlas has survived for such an extended period is remarkable, as interstellar space is not a hospitable environment for delicate icy bodies. The comet must have endured the harsh conditions of deep space, including exposure to cosmic radiation and the occasional gravitational disturbance from passing stars or molecular clouds. The discovery of 3I Atlas raises the possibility that interstellar objects like it are more common than previously thought, hinting at a vast, unseen population of comets and asteroids that drift silently through the cosmos. The implications of these discoveries extend beyond the study of individual comets. They contribute to our broader understanding of the universe and the processes that govern the formation and evolution of planetary systems. The fact that C2025 R2 SWAN and 3I Atlas have both been observed and studied in such detail is a testament to the advancements in astronomical technology and the growing capabilities of modern observatories. Instruments such as the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories have enabled scientists to analyze the composition, structure, and behavior of comets with unprecedented precision. These observations not only enhance our knowledge of cometary science, but also inform our understanding of the broader cosmic landscape, including the distribution of material in the galaxy and the frequency of interstellar encounters. Furthermore, the study of comets like C2025 R2 SWAN and 3I Atlas contributes to the search for extraterrestrial life and the study of the origins of organic molecules. Comets are known to carry complex organic compounds, including amino acids and other building blocks of life, raising the possibility that they played a role in delivering these materials to Earth in the early stages of planetary development. While C2025 R2 SWAN has disintegrated, preventing a direct analysis of its organic content, 3I Atlas remains intact, offering a unique opportunity to investigate the chemical makeup of an interstellar comet. Future observations of 3I Atlas may reveal new insights into the types of organic molecules present in other planetary systems and how they compare to those found in the solar system. Such discoveries could provide valuable clues about the universality of life's building blocks and the potential for habitable worlds beyond our own. The journeys of C2025 R2 SWAN and 3I Atlas also highlight the importance of continued exploration and observation in the field of astronomy. As technology advances and new telescopes come online, we are likely to detect more interstellar objects and comets from the Oort Cloud, expanding our understanding of the universe. These discoveries will not only deepen our knowledge of cometary science, but also challenge existing theories and prompt new lines of inquiry. Whether through the study of cometary disintegration, each new observation brings us one step closer to unraveling the mysteries of the cosmos. As we bring this cosmic journey to a close, we are left with a profound sense of awe and humility. The stories of C2025 R2 SWAN and 3I Atlas remind us that the universe is not a static, unchanging expanse, but a dynamic tapestry of motion, transformation, and connection. These comets, born from the distant reaches of the Oort Cloud and the depths of interstellar space, have traveled for thousands or even billions of years to cross our path in the sky. Their fleeting appearances serve as a humbling reminder of the vastness of time and space, and the incredible distances that separate celestial bodies. Yet, despite the immense scales involved, these comets have brought us closer to understanding our own cosmic neighborhood and the broader universe beyond. The study of comets is more than just an academic pursuit. It is a window into the origins of the solar system and the processes that have shaped the planets, moons, and other celestial bodies we see today. C2025 R2 SWAN, with its journey from the Oort Cloud, offers a glimpse into the primordial material that once swirled around the young sun. Its disintegration near the sun is a natural endpoint in the life cycle of a comet, a final act in a journey that began in the frigid outskirts of the solar system. In contrast, 3I Atlas, an interstellar traveler, carries with it the history of another planetary system, a relic from a time when the Milky Way was younger and the conditions for planet formation were vastly different. The fact that we have been able to observe and study these comets is a testament to the power of modern astronomy and the ingenuity of scientists who have developed the tools and techniques necessary to peer into the farthest reaches of space. These comets also challenge our perception of time. To the human mind, 40,000 years may seem like an eternity, but in cosmic terms, it is but a moment in the grand sweep of history. 3I Atlas, with an estimated age of 7 to 14 billion years, predates the formation of the solar system itself, reminding us that the universe is far older than we often imagine. The idea that an object from a distant star system has crossed paths with our own is both exhilarating and sobering. It reinforces the notion that we are not alone in the universe, and that the same fundamental forces that govern our world also shape the cosmos at large. As we reflect on these cosmic wanderers, we are also reminded of our own place in the universe. The Earth, with all its complexities and wonders, is just one planet in a vast and intricate system. The comets that grace our skies are not just distant objects, they are messengers from the past, carrying with them the echoes of cosmic history. They remind us that the universe is not indifferent to us, but rather that we are a part of something far greater. The study of comets, therefore, is not merely about understanding celestial mechanics or planetary formation. It is about understanding ourselves, our origins, and our connection to the cosmos. The next time you look up at the night sky and spot a comet streaking across the heavens, remember that you are witnessing a journey that spans millennia, perhaps even billions of years. You are seeing a fragment of cosmic history, a reminder that the universe is alive with motion and change. The comets of today will one day fade from view, but their stories will live on in the data we collect, the knowledge we gain, and the inspiration they provide. As we continue to explore the cosmos, we are not just observers, we are participants in a grand unfolding story, one that connects us to the stars and to the infinite expanse of time and space.